So let's just get right started and get some additional practice. What if you were given x squared plus y squared is equal to y squared over x squared? Now notice that this equation, it's not already solved for y. So if it were already solved for y, you could just take derivatives in the normal manner. But since it's not already solved for y, we have to use our implicit differentiation. So what we're going to do is just go left to right, taking derivatives of every term using the rules that we have outlined in the last section. And just to refresh your memory, anytime you come across an x term, since we're taking this derivative dy with respect to x, anytime you come up to an x, you just take the derivative in the normal way. All right, just like before. Anytime you come up on a y term, something like that, you take the derivative in the normal way, but then you have to multiply it by dy dx because you don't know how y varies with respect to x. You know how x varies with respect to x because it's itself, so you really don't ever have to write that down, but we have to explicitly write it out for these terms. So we look at this guy and we say, all right, derivative of x squared is just 2x. Okay, so far so good. Then we look and we say, well, the derivative of 2y would be 2y, the same exact procedure, subtracting 1 off the exponent, but then we have to multiply by dy dx. And this is the chain rule in action, and we've talked about that in the last section. Okay, and then on the right-hand side, we have a quotient. We have y squared over x squared. So we're going to need to take the derivative of this entire thing, but this is a division going on here, so we need to use the quotient rule. So what we're going to do is bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So what we're going to have is the bottom times the derivative of the top. What is the derivative of y squared? It would be 2y dy dx. Exactly what we wrote here. So this is bottom times the derivative of the top minus the top, which is this guy, times the derivative of the bottom. What's the derivative of x squared? Is just 2x. All over the bottom squared. So for right now, we'll write it as x squared squared. All right, so bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. That's how we did that. All right, now let's go ahead and simplify a little bit. There's not much to do on the left-hand side, so we'll just rewrite it. So we have 2x plus 2y dy dx is equal to. And then here we have 2x squared y dy dx minus 2xy squared. And on the bottom, we just have x to the fourth power. All right? So what we're going to do next is just simplify this expression. Now, what we really ultimately want to do is solve for this term, dy dx. So we need to manipulate this and collect terms on both sides so we can basically isolate and factor that out. So the biggest thing in my way is its denominator. So what I'm going to do is multiply both sides of this equation by x to the fourth power, so it'll disappear on the right-hand side. So we multiply by x to the fourth, and on the left we'll have 2x to the fifth, because we're multiplying by x to the fourth, so we add the exponents here. Then we'll have 2y times x to the fourth, because we have to multiply both terms by x to the fourth. Don't forget your dy dx. And on the right-hand side, we just need to rewrite this stuff here. So let's go 2x squared y dy dx minus 2xy squared. So ultimately, like I said, we want to solve for dy dx. So we need to sort of get those on the same side of the equal sign. So I'm going to do a couple of manipulations here in one step. First thing we're going to do is we're going to take this 2x to the fifth and we're going to move it to the other side. And then we're also going to take this entire term here and move it to this side. We're not going to do too many things at once, so let's go ahead and write it beginning with this term. 2y times x to the fourth times dy dx. Now we're subtracting this term over, so minus 2x squared y dy dx. All right, now don't forget we move this over here, so we're going to have equals negative 2x to the fifth minus 2xy squared. Make sure you understand. All we did was flip some terms around. We take this guy, subtract it over there, that puts it there. We take this guy, subtract it over here, puts it over here. The only reason we're doing this is so we can basically solve for here. So let's factor out dy dx. You can treat dy dx as any other variable. It's a quantity. It's the derivative. So we can factor it out over here on the left-hand side. dy dx. And on the inside, we just write everything else. We have 2y x to the fourth power minus 2x squared y. So this is exactly the same thing we have on the left. On the right, we have negative 2x to the fifth minus 2xy squared. All right, so I think you kind of see where we're going with this. To find dy dx, we just divide both sides by this entire quantity, and then we've isolated our variables. So we have dy dx is equal to, on the top we're going to have this quantity over here, so we'll have negative 2x to the fifth minus 2xy squared, and underneath it we'll have this entire quantity because we've divided, so we'll have 2y x to the fourth minus 2x squared y. And that really is the answer. But if you look carefully, you'll see that you can simplify this because we have a 2 everywhere, so we can cancel them out. Another way to think about it, if you don't see that, is you could factor a 2 out of the top and you can factor a 2 out of the bottom, so you'll have 2 over 2, so they'll cancel. But when you have the same quantity in every single term of a rational expression like this, a fractional thing, you could just strike through them because they basically all divide out, but they have to be everywhere. All right? Now let's look and see what we have. Do we have a y everywhere? We have y here, we have y here, we have y squared here, but we don't have any y's here. You're unable to cancel these y's because they're not common to both numerator and denominator, because it's not here. But the x's are. You have x to the fourth, x squared, x, and x to the fifth. So the only thing you can cancel here is just a single x, because this is a term here where we only have one x, because that's all we would be able to factor out in the top and also in the bottom. So we can cancel this x entirely. We can, in this x squared, we can cancel the x squared, leaving ourselves with just one x. Over here for the x to the fourth, we can cancel one of these guys, making it x to the third power. And then this x to the fifth, we can make that x to the fourth power. And I know that's a little bit messy, and you may have different ways of writing it on your own paper, but when you do this, the final answer, dy dx, is equal to negative x to the fourth power, negative x to the fourth power, minus y squared, minus y squared. And on the bottom, you have y x to the third, y x to the third, minus x y, minus x y. So what we have is minus x to the fourth minus y squared over y x cubed minus xy, and this is the answer. And notice that this derivative that we've calculated involves x's and y's, which is different, just like we talked about in the last section, a little bit different than all the other previous sections, when usually your derivative is a pure function of x. Well, the reason those were all pure functions of x is because our original function, our problem, was defined f of x. It was all predefined for us and nicely solved. When you don't have that luxury, then your original function is defined implicitly, so your derivative is going to be defined implicitly also. So if you wanted to find the derivative at a certain point on this curve, you'd have to supply x and y, which would be the point on that curve, and you would get the derivative back at that point, which is exactly what we're going to do in this next problem here. Let's go ahead and work a problem where we're given a relation. So in this case, let's say we have x squared plus y squared is equal to y. And let's find dy dx at 0, 1. So this is slightly different, but it's just a natural extension. What we're going to do is find the derivative dy dx, right? But then once we get the answer, we want to evaluate that derivative at a given point on the curve. So we're going to actually calculate a numerical value of the slope of the original curve, or the slope of the line tangent to the original curve. So we need to use implicit differentiation here. This guy is just an x squared, so you take the derivative, we'll get 2x. All right, and the next term, we take the derivative of this, we'll get 2y, but then we have to multiply by dy dx, because we don't know how y varies. All right, and then over here on the right-hand side, the derivative of y would just simply be 1, but we need to multiply by dy dx. So anytime you run into a y, you have to tag on a dy dx. That's sort of the rule there. So what we're going to do is we want to solve for this quantity dy dx. So let's move this term over here, and let's move this term to the other side. So what we'll be left with is 2y dy dx. Let's subtract this term over, so it'll be minus dy dx. And let's subtract this term over to the other side, negative 2x. All right, now to continue making progress, we need to factor out this derivative. dy dx, let's pull it out. On the inside, you'll have 2y minus 1 is equal to negative 2x. So the final solution, really, is to divide both sides by this quantity, and then we've solved for dy dx, which is what we want. So dy dx is equal to negative 2x over 2y minus 1. Negative 2x over 2y minus 1. But the problem didn't say just find the derivative. It said evaluate the derivative at 0, 1. So all we do is we say, okay, at 0, 1, here's what we get. dy dx is equal to 0 for x, so we have negative 2 times 0, 1 for y, so 2 times 1 minus 1. So here we have 0 on top, and here we have 2 minus 1 is 1 on the bottom, so we get 0. So the answer is 0. So we say dy dx is equal to 0 at the point 0, 1. That would be really how you write it down. So I just want to sort of illustrate this type of problem because it really drills home and tells you what we're supposed to be doing here. We have a function. We take its derivative implicitly, we arrive at the answer. This is what you would have circled in the previous problems. In this particular problem, we're saying let's take it a step further. Let's pick a specific point 0, 1 on this curve and plug it in and find out what the slope of the curve is at that point. And when we put it in there, it means the slope of that curve at that point is 0. What does that mean? What is a slope of 0? Slope of 0 means totally flat, not slanted at all. So it's totally flat. So if we were to plot this, pick all these points, then we would find that when we look at 0, 1, it would be flat at that point, right? Now, one more thing I want to say is that this guy, this original equation that we were given, it's not already pre-solved for y, we know this, but you can still find points on this curve. It's still a curve. I mean, in fact, if you put 0, 1 in here, you'll see that it satisfies the original curve. 0 for x, so we're going to get 0 here, 1 for y. So we'll have 1 here, 1 squared is 1, a 1 here. So if you want to look at it this way, you'll have 0 plus 1 equals 1. Right? So 1 equals 1. So the equality is satisfied. So just because it's not solved in terms of a function f of x, don't get too weirded out by it. It's just, you know, some of these guys are implicitly defined. They still have points x, y that fall on a curve that you can graph. It's just not quite so easy to visualize it or punch it in your graphing calculator, but it still exists. This implicit differentiation method allows us to find the derivative of these guys you know, without knowing the f of x defined function ahead of time, right? So let's keep going and ratchet up the complexity just a little bit. Let's say we have x cubed plus 2xy is equal to 5. And what we want to find is dy dx at the point 1, 2. So this is a point that falls on this curve. If you put 1 in for x and 2 in for y, you'll find that it satisfies. Let's do it. 1 for x, so we're going to get 1 and 1 here, 2 for y. So this is 1, this is 2 times 1 is 2, times 2 is 4. So 1 plus 4 is 5, so it does satisfy this relation. So that point is just simply a point that falls on that curve, right? Let's take the derivative. Let's go term by term. This guy is just x cubed, so the derivative of that's going to be 3x squared. This guy is going to be a little bit more involved because we have x times y. So we have two things multiplied together. We have to use the product rule. So this is function 1 and function 2. And so the way you would do it is first times the derivative of the second plus the second times the derivative of the first. So what you'll get is 2x. What's the derivative of the second function, y? Well, it's going to be 1, but then we have to have dy dx, right? Because we're taking the derivative of y like that. Plus the second function y times the derivative of this guy. What's the derivative of this? It's just simply 2. So we put that there. And on the right-hand side, we take the derivative of this constant, we get 0. Make sure you understand that. First times the derivative of the second term, that's what this is. Plus the second term times the derivative of the first term. So we're just using all of the rules that we have kind of defined thus far. So what we're going to have, just to rewrite it, is 3x squared plus 2x dy dx plus 2y is equal to 0. And we want to solve for dy dx. That's what we want to do. All right, so let's go ahead and move these terms over on the right-hand side. So 2x dy dx is equal to, let's subtract negative 2y, let's subtract negative 3x squared, minus 3x squared. And to finally solve for dy dx, we just divide by this. So what we're going to end up with, dy dx is equal to, this numerator now, negative 2y minus 3x squared, over this guy, 2x. So this is the answer. This is the derivative of this function. But we want to calculate this derivative at a point 1, 2. So we say at 1, 2, we get the following thing. dy dx is equal to, well, y is 2, so we'll have negative 2 times 2 minus 3, x is 1, so we'll have 1 squared times 2x, so 2 times 1. So let's switch colors here. So what we're going to have over here is, this is negative 4, this is minus 3, and on the bottom we'll have 2. So ultimately what we have here is negative 7 over 2, negative 7 over 2. So the way you would write that is dy dx at the point 1, 2 is equal to negative 7 halves. Negative 7 halves. So if you had all of the points that lied on this function, and if you had graph paper and you plotted them all and you looked at what the function looked like, if you go to the point 1, 2 over there, 1, 2, right, and look at the slope of the curve that's tangent to that guy, then what you're going to find is it's going to have a negative slope, right? So it's going to be slanted in the negative sense, right? So from you looking from my point of view, if you remember, a positive slope looks like this anytime we have a positive slope, and negative slopes go the opposite direction like this in red. So if you were to plot this function and look at the line tangent to that curve at that exact point, it would have a slope more or less slanted that direction. All right, so that's basically all we have with that problem. Now our final problem is going to be a little bit more involved. It's going to be a little bit more complicated. We sort of saved the best for last, right? But it's not that hard. Let's say we have square root of x plus 1 times square root of y plus 2 is equal to 8. And we want to find dy dx at 1, 4. Right? So first thing you should notice is that you have these square roots running around everywhere. So we don't really want to have square roots, but what I want to do is sort of write out the product rule. We have a function here times a function here, and in the process we're going to get rid of these radicals and write them as powers of 1/2. So what you have is the first quantity, so you'll have x to the 1/2 plus 1 times the derivative of the second quantity, like this. First times the derivative of the second plus the second quantity, y to the 1/2 plus 2 times the derivative of the first, x to the 1/2 plus 1 prime equals 0, because we take the derivative of the right-hand side and we get 0. So make sure you understand, first times the derivative of the second plus the second times the derivative of the first. We just replaced the square roots everywhere with powers of 1/2. All right, so let's go ahead and take these derivatives and see what we get. So what we're going to have over here is x to the 1/2 plus 1. What do we have inside here? We're going to have 1/2 y to the negative 1/2. The derivative of this term, 0, so it doesn't count, and we multiply by dy dx, because that's a y variable that we're dealing with. And then over here, let's just recopy this, y to the 1/2 plus 2, and then inside here, it's just 1/2, taking the derivative, x to the negative 1/2. This derivative is 0, so it doesn't play. So we leave it like that. Now what we ultimately want to do is solve for dy dx. So what we're going to do is, notice that all of this stuff is multiplied together over here, and all of this, they have an addition here. So let's move this entire quantity over there. Basically, let's solve for dy dx. dy dx is equal to, I'm going to introduce a negative sign when I move this whole thing over here, so I'm going to have negative y to the 1/2 plus 2 times 1/2 x to the negative 1/2, all divided by, because I moved this over there, that's why I made it negative, but then to solve for dy dx, all of this stuff we need to divide by to get it over here. So what we're going to have is x to the 1/2 plus 1 times 1/2 y to the negative 1/2. Make sure you understand that because you won't get any farther in the problem if you don't. Basically, we're just solving for this quantity. So we take this entire term, we move it to the other side, that makes it negative, and then we have all this stuff sitting out in front of the dy dx, this entire parenthetical plus this guy, so we divide by both of them, and that's why they end up on the bottom over there. All right, so the first thing that we see is that we have a 1/2 in the top and a 1/2 in the bottom, so they are going to essentially disappear. And to make the next step, let's go ahead and convert these 1/2, these powers of 1/2 back to radicals, because we've already taken the derivative, and that was the reason we did it, to convert them back to 1/2, because it's easier to take derivatives. But for now, let's go ahead and convert them back. So I have a negative sign on here. This is the square root of y plus 2. Okay, so what we want to do here is we have the negative, and then we have this term here. Notice that here we have x to the negative 1/2, and here we have y to the negative 1/2. So let's move this y upstairs and make him positive 1/2. So that'll give us square root of y on the top. And on the bottom, we'll have this term, x to the 1/2 plus 1. And then this x to the negative 1/2 will come to the downstairs and become positive. So it'll be square root of x. So all we really did was we took this term, brought it downstairs, and made it x to the positive 1/2. We took this guy and brought him upstairs and made him y to the positive 1/2. So that's why we have those radicals like this. All right, so the answer is negative square root of y plus 2 root y over square root of x plus 1 times square root of x. Now there's one more thing we can do to simplify. dy dx, it's sort of trivial, but if we multiply this y in, it'll be square root of y times square root of y, which is the same as y to the 1/2 times y to the 1/2. So what we'll have on the inside is y to the 1 power, so y, plus 2 times the square root of y. Whoops, times the square root of y, like this. That will be on the top. On the bottom, if we choose to multiply the square root of x in, we're going to get the same thing. This is x to the 1/2, this is x to the 1/2. You add them together, you get x to the 1 power. X plus square root of x. So make sure you understand that. The only thing going on here is we multiply this in here, that gives us y. This gives us 2 times the square root of y. This gives us x, and this gives us the square root of x. So this really is the answer. But if you're interested at the point 1 comma 4, then dy dx is equal to negative y is 4 plus 2 times the square root of y, which is 4. And on the bottom, you'll have x, which is 1, plus the square root of x, which is 1. And so over here on the top, you'll have negative 4 plus, this is going to give you a 2. Square root of 4 is 2. 2 times 2 is 4. So let's just write it as a 4. On the bottom, you have 1 plus 1, which will give you 2. So on the top, you have negative 8 over 2, which is negative 4. So the way you would write this in total is that dy dx at the point 1 comma 4 is equal to negative 4. So again, it's a negative slope, so it's sloping in the same exact direction as the last problem. It's quite a large slope, though. It's not even fractional, so that means it's fairly steep. So it's the same process going on. It's just, you know, first of all, these radicals trip up a lot of students. Just do yourself a favor, convert them to fractional exponents of 1/2. So you have x to the 1/2 here, and so you just run it all through. And what that allows you to do when you take these derivatives is, it's much easier dealing with an exponent, because then you could subtract the exponents and keep it all straight. Once we did the derivative, then we solved for the derivative that we're trying to find, dy dx. Once we got to this point, there was no point. You could leave it in terms of fractional exponents, but it's just as easy to convert it back to radicals, so it looks a little bit cleaner. And then get your final answer all squared away, plug in the value that you have. Now, if you really wanted to, you could leave it fractional exponents all the way to the end. You're going to get exactly the same answer. So there's a little bit of latitude in how you choose to do it. But usually, if I have radicals in the original problem like this, then I try to get my final answer in terms of radicals to put it in the same form. But there's nothing Nobody says that you have to work with radicals throughout the process. Just do the conversion, take the derivative, and then convert back. It's just much, much easier that way, in my opinion. So here we've covered some additional problems in implicit differentiation. It's a skill that a lot of students don't quite understand at first, but it's not that hard. We've tried to explain why the chain rule comes about and why it works. We've talked about that in the last section at the beginning of also this section, but practically speaking, anytime you run up against a function of x like this, when you're taking the derivative, you just take it normally. When you run up against a y function, you take it normally, but you tag a dy dx. You multiply by dy dx, and then you just solve your equation for dy dx. The answer that you get is almost always going to contain x's and y's because this is an implicitly defined function that's not already pre-solved for y, in other words. So you're going to see x's and y's running around this guy. That's about it. Practice these problems. Practice additional problems in your textbook. Follow the procedure I've outlined here, and implicit differentiation will not be a big deal. You just need to practice it and do enough problems so the process becomes mechanical and natural, and sharpen your algebra skills, which is what this whole entire course has been about. Most of this problem is algebra after you get past the simple derivative part. And then with that, you'll do just fine on your exams, on your homework, and on your tests.
Learn anything at mathandscience.com.